Hi everyone, my name is Prakhar Ganesh and today I'll be presenting our work on the impact of machine learning randomness on group fairness in collaboration with Hongyan Chang, Martin Strobel and Reza Shokri. Let's jump right into it. As most of you might be familiar, machine learning has a fairness problem and can propagate biases if deployed unchecked into the real world. Research around these biases have led to the rise of fair machine learning. One of the central pillars of fair machine learning is being able to empirically evaluate the biases in a ML model. However, recent works in literature have shown high variance in fairness scores across multiple training runs simply due to the randomness in training. This variance means that existing trends in model fairness can become unreliable if one does not properly account for the randomness. For instance, when comparing various bias mitigation techniques in this example, one can draw unreliable conclusions if one does not take into account the high fairness variance across random seeds. Appropriately capturing the fairness variance is extremely important to truly capture fairness trends in ML models. The existing approach in literature to overcome the impact of randomness is to simply execute multiple training runs. However, simply executing multiple runs is quite expensive and can raise the computational requirement to do fair machine learning research. Moreover, it lacks any understanding of the underlying cause of fairness variance. In our work, we aim to find a computationally efficient alternative to the same by uncovering the real cause behind high fairness variance. Let's start by decoupling the various sources of randomness during training. We will talk about two canonical forms of randomness, weight initialization and data reshuffling. In any standard training pipeline, we start neural network training by randomly initializing the model weights. We then start updating the model parameters by performing gradient updates using the training data. At every epoch during training, the training data is randomly shuffled and the gradients calculated to perform a single epoch of model update. After sufficient epochs of training, the model is finally evaluated on a separate test set. While there are many other forms of randomness that can be introduced into this pipeline, the two sources of randomness that are present in any standard setting are weight initialization and random reshuffling. For our first experiment, we will talk about two settings in particular: fixed data reshuffling, which refers to multiple training runs starting from different initializations but being fed the same data order during training, and fixed weight initialization, which refers to multiple training runs which all start from the same weight initialization but are fed different data orders during training. We record the distribution of fairness scores at every epoch across 50 unique runs under these two settings. Interestingly, we find significantly lower variance across training runs at any one epoch under fixed data reshuffling, even though we do see high volatility of fairness scores across consecutive epochs. This shows that fairness scores are clearly dominated by the data order. The same conclusions can also be drawn from the fixed weight initialization setting. Clearly, it is indeed the random reshuffling that dominates fairness scores, and there is an immediate impact of data order on fairness, as seen by unstable fairness scores even in a single training run. Next, we try to understand why are underrepresented groups more sensitive to randomness in model training. To better understand the variance at a granular level, we start by measuring prediction uncertainty for data points using the Monte-Carlo dropout method. Monte-Carlo dropout measures prediction uncertainty by performing multiple passes through the model with dropout enabled even during inference. We record the distribution of model predictions across different forward passes, and the standard deviation is labeled as the prediction uncertainty for that particular data point. We then repeat the same for all data points and record their prediction uncertainty. Before we jump into the results, we first plot the distribution between various subgroups in our dataset, which is the income dataset. we can see that the positive labels for the group female are significantly underrepresented as compared to all other subgroups, especially the negative labels from the group female. Next, we measure the uncertainty in prediction for all data points and plot the cumulative distribution of prediction uncertainty across data points for each group separately. The prediction uncertainty results reflect the trends of the dataset representation. That is, the more well represented a subgroup is, the less its distribution is skewed to the right, and thus it contains less percentage of data points with high uncertainty. It is clear that underrepresented groups in the dataset end up with high prediction uncertainty and thus become far more vulnerable to even minute changes in the model weights. Now that we have studied the relationship between fairness, variance, and data order, we can apply our understanding and obtain several interesting results. We first start with our original question. Can we make capturing variance across multiple training runs more efficient? To understand this, we define two distributions of fairness. Fairness across multiple runs and fairness across multiple epochs in a single run. As we have previously highlighted, the fairness score at any epoch is dominantly affected by the data order of that particular epoch, and thus the empirical distribution of fairness scores across multiple runs should be equal to the distribution of fairness scores across epochs in a single run. To verify this, we plot the following 6 distributions. The first 3 distributions record fairness variance across multiple runs at a fixed epoch, and the next 3 distributions record fairness variance across multiple epochs in a single run for 3 different runs. While recording variance across multiple runs is significantly more expensive computationally, the fairness distribution could be easily studied by just capturing several checkpoints in a single training run. This gives us a significantly more efficient alternative to blindly running multiple trainings. Given the immediate relationship between data order and fairness, we propose to create custom data orders that can manipulate fairness scores of the model. We hypothesize that the distribution in the most recent gradient updates for a model can temporarily change the loss landscape and nudge the group level accuracy to that distribution. More specifically, we perform experiments with two specific custom data orders, namely equal order, designed to improve model fairness, and adversarial order, designed to adversarially introduce bias into the model without affecting the overall model accuracy. More details on the custom data order design are present in our paper. We will now record the effectiveness of our custom data order. We start by training a model till convergence and report the baseline results. We then take the checkpoint at the final epoch and pass it through a single epoch of equal order or adversarial order respectively. Firstly, it can be noted that despite the additional epoch of our custom data order, the F1 scores have not changed significantly. However, looking at the fairness scores, one can see clearly that only a single epoch of equal order can drastically reduce the bias present in the model, while only a single epoch of adversarial order increases bias far greater than even in the unconstrained settings. Overall, we show that custom data orders created based on the desired data distribution can significantly yet predictably alter the model's fairness scores in only a single epoch of training. To sum up our work, we would like to reiterate the following major takeaways. We studied the two commonly adopted forms of randomness in model training and found that data shuffling has a dominant and immediate impact on model fairness. We found that prediction uncertainty of minorities is significantly higher, which makes them far more sensitive to changes in the model weights. Based on our observations, we showed that instead of executing training runs to capture overall fairness distribution, one can instead simply study the model behavior across epochs in a single run. Finally, we showed how to create custom data orders that can help one minutely control and manipulate group level performances and thus in turn the fairness scores in only a single epoch of training. That's all from me. Thank you for your time.